Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Stephen Newberry, a signal integrity and power integrity engineer at Chipletz. Stephen's path into engineering started in the US Coast Guard, where he worked hands-on as an electrician. That experience sparked his curiosity for design and eventually led him to specialize in ensuring that high-speed signals move across chips and boards without corruption. Beyond his day job, he also shares his insights through a blog where he writes about the challenges and advances in the space. In this episode, we dive into the role of simulation in SIPI engineering, why accuracy and speed are such critical bottlenecks, and how emerging technologies, from AI-assisted solvers to low-cost open-source tools, could reshape the way engineers design and test electronic systems. Whether you're working directly with circuit boards or just curious about how simulation impacts the technology all around us, there's something here for you. Without further ado, let's get started. What is it exactly that you do?
That's an awesome question. So signal integrity and power integrity, in the way that I've formed them over the years, it's a bit of a niche in digital hardware design. So it touches on a lot of different aspects. If you take a generalist hardware engineer who designs printed circuit boards, they have to worry about a whole lot of things. They have to worry about software, the proper schematic design, the way that all of the parts are going to interact, the way that their board is going to interact with the broader system. But if you drill down, there's one particular detail that I really just fell in love with, and that's how are we getting these super high speed multi-gigabit signals from one chip to another or from one board to another without corruption. And I think that really boils down what signal integrity is, and power integrity goes into it, because if your power rails, if your voltage has fluctuations, ultimately that'll show up in your signals as well. So they're all interrelated.
So for the layman out there, what kind of devices is this kind of signal integrity, power integrity in?
It's in anything electronic. Anytime you have one chip talking to another chip, whether that's on one single board, this could be as simple as the CPU on your mobile phone that has to talk to some memory on a different chip there within the same device, or it could be from one system to another crossing cables, something as simple as Ethernet networks in your home or your office, anything like that.
And from what I understood, you weren't always geeking on the designs themselves, but more of a hands-on guy. Might still be. Could you tell us a bit about your background in this field?
Yeah. Oh yeah, absolutely. I'm still hands-on. I was just fixing a friend's lawnmower last night. I love to get my hands dirty with anything I can. But you're right. I haven't always been on the design side, and I really credit my time in the Coast Guard with where I am today for a bunch of different reasons. So many years ago now, I was in the Coast Guard and I was an electrician. And the wonderful part about that is I got an extremely good electrical fundamentals education there. I think really for what it is, it was phenomenal, giving me an understanding of how electrons work, how these circuits work from a basic level. And what was nice about that also is that I got that hands-on experience with troubleshooting and repair. And I think a lot of engineers don't have that experience. So when they're working on circuits that have problems, it can be a little bit of an exercise to try to debug where exactly a problem is coming from. But it was a little more than that got me into design. I loved the work that I did in the Coast Guard. I did repair work on boats. I worked on lighthouses and buoys and everything. It was really exciting. And I had a few particularly troublesome issues on one of the boats that really made me mentally think about, hey, why is it designed like this? Why would somebody make the decision to create a device that caused the technician troubles while repairing? And that gave me my first motivation to look into getting into engineering itself. Now, alongside that also was the fact that education here in America is very expensive, and the military gives a wonderful benefit. And without that benefit, I really wouldn't be here today as well. So that's what kicked it off. And I was fortunate enough to get into hardware work just like I wanted to after college, and I've been able to drill down my career into sort of laser focus into this area of signal and power integrity.
So how does simulation fit into that then?
Yeah, simulation and measurement, they go hand in hand in signal integrity. There's what you expect to see when you're designing the board, and then what you actually see after your board is designed. But simulation, I find that I spent a lot of time in simulation, and that's because the more time you can spend up front in simulation, ideally the less time you're going to spend measuring and hopefully not debugging any particular issues that you have after something is fabricated. So I spent a lot of time simulating to just get a comprehensive understanding of how all of the systems on my board or on my package or on my device are going to interact with each other to make sure we avoid any of those issues down the road.
You said you get a comprehensive understanding. Is that really what you get? Do you really see exactly what you expect to see?
I wish I could say that I could simulate every single thing going on a single board or a single package all at the same time, but absolutely we can't do that. That's way too complex. But when it comes to simulating what we expect, for the most part, I'm able to match up simulation and measurement reasonably well. And the reason that you can do that is because you put a lot of effort up front into finding your material properties. What is the dielectric behavior of your different circuit board materials and things like that. It does help.
Yeah. So what kind of, let's say, both pros and cons do you face when exactly simulating this? You also already mentioned that the complex nature, maybe not being as thorough as you would like in an ideal world.
Yep.
What else? Both good and bad.
I guess to start with the cons, the bad, it's very time intensive. So one in particular, there's not really a good universal data exchange format per se. In the world of circuit boards, we have ODB++ as a data exchange format, which is generally readable across different software tools, but it's not perfect. And even when you bring it in, there's still a lot of upfront work required to get your simulation, all your layers stack in your circuit board and things like that, everything exactly the way you want it. There's a lot of upfront work, and then just the speed of simulation itself. It's computationally expensive, and so when you're working on extremely complex devices or very high frequencies, either of those are going to cause the mesh to be really blow up, really be a very large mesh, and that takes time. So I've had simulations on some devices that are running days or even a week or two.
So let's say you had the famous magic wand in your hand, and
Yes.
you could whip it, and you could change one single thing. Now, what would that thing be?
I do think computational speed would be the one thing if you make me really drill down into one thing, and there's a good reason for that. Simulation is often iterative. You work on something, you simulate, you see something you want to fix, so you re-simulate, and so that turnaround time, the ability to simulate, investigate, re-simulate, that loop, the tighter you could make that, the quicker you can get your design cycle done with an optimal design there at the end.
So back to quickly touch on broadly the whole industry of signal integrity or power integrity. Is that a evolving field? So is there advancements going on, or has it been sort of plateaued in any sense in the past decades or years?
There's definitely advancements that I see from my perspective from a couple of different aspects. So as a field itself, I think it's relatively new. Compared to other disciplines within electrical engineering, I don't really think that term signal integrity appears until maybe the late 80s or early 90s. But as to how it's been evolving over time, the simulation tools themselves have been adding excellent capabilities over the years. So that does help a lot. You have the the incumbent simulation tools, EDA tools that are adding things, say, for example, some optimization tools that have AI under the hood to optimize parameters and things as you're simulating. But the other way I'd say that simulation is evolving, or rather the field of signal integrity, is in technology itself. So if you look at certain interface standards, most people might be familiar with PCIe. It's commonly used on your graphics cards in your PC and such. That standard attempts to double every time they come out with a new generation, every couple of years. So if you're on, say, Gen 3 a few years ago, maybe a decade ago, that was 8 gigabits per second. Gen 4 was 16, Gen 5, 32, and they're already announcing and working on 6, 7, and I think I even saw an announcement for 8. And every single one of those, they're doubling the amount of data that's getting transferred. And that's an incredible challenge. So all of the tools have to keep up with it. Manufacturing processes have to keep up with it. That's something that maybe people don't consider as much, as if you're using the same processes to build your circuit board that you were 10 years ago, it's probably not feasible to design something that is going to have good signal integrity. So the manufacturers have to figure out how to get smaller traces, wires on your circuit board, smaller connectors to interconnect things. All of that goes together.
Well, do you foresee something changing? Well, again, speaking broadly about the industry in the near term future, let's say 3 to 5 years.
Yeah, absolutely. And I would say the biggest driver there is probably artificial intelligence. So one thing that I see is a ton of different startups and small companies in the simulation space that are sort of maybe AI under the hood, but are working to develop different methods to speed up simulation, whether that's with like pins, as you guys talked about on your last episode of this podcast, or other neural net based solvers, things like that. And I think that's good for the industry, because I think it's going to create some competition amongst maybe the incumbent simulation tool vendors and everything. So that's always, I mean, competition is always good for the users of the tools. It means we'll get maybe lower prices or more features, things like that. But overall, I do think there's a lot of promise in AI. I worked on AI-based augmenting field solvers with AI as part of my master's thesis, and I really see a future where some of those technologies are able to speed up that turnaround time, as I mentioned before, and get simulations to run faster.
And what kind of effects would it have on the devices themselves, or would it have a major impact on the let's say the microchips?
Yeah, I could see a major impact, because you're able to do things like, if your simulations are more accurate and faster, maybe you're able to get away with a lower cost manufacturing process to still achieve the same performance that you wanted. So thereby reducing costs to the end customer. That's one option. Or alternatively, keeping the same cost, keeping the same, keeping all other things the same, you could increase performance beyond what was originally expected, or just increasing time to market, getting devices and products out to customers faster. I think all of those could be feasible.
Yeah, like what I was trying to grasp, that was a great answer, by the way. I maybe misspoke a bit. What I was trying to grasp is that when you increase the signal integrity performance, how does that affect the end device of, let's say,
Okay.
a microchip?
Yeah, I understand what you mean. One, I guess, one of the most obvious to me is that you can lower power consumption. If say your signal integrity, a lot of devices will have extra circuitry to perhaps boost signal strength to improve signal integrity. If you have better SI performance overall, or maybe a better, more accurate prediction up front, then it could be perhaps possible to reduce the amount of power required to boost those signals, overall lower power consumption. That's one that jumps to mind for sure.
Great. You are kind of it's seemingly keen to this topic, as you do some writing on the whole topic of your on your website. So could you tell us a bit about that? So what motivates you to sort of share the knowledge that you have?
Oh yeah, I think there's two reasons. So the first one is that I'm really grateful for the mentors I've had in my career. I've had some really excellent people guiding me as I grew as an engineer and everything. And so I want to be able to do that for other engineers as well. Provide information, a way for them to learn, things like that. But then second of all, if we as an industry want to continue developing cutting edge devices and technologies, we're not going to be able to do that without relying on all of the work that has been done before us. And so we have to continue building on that. So everything I try to write about, it's things that I've learned from others, and I just want to build on that, and I just want to share it. That's really my motivation.
Are there any myths or surprising facts that you would like to say to people who are maybe not experts in the field about signal integrity?
That's a good question. Let's see. I'll have to think about that one for a second. Myths or surprising facts. I guess, one thing that is surprising, sometimes signal integrity, sometimes your circuit can work when you really didn't expect it to. There's a famous demonstration it's a few decades old now about running Ethernet over some barbed wire. It's a demo that I've seen a photo of and everything. So there are times when circuits will still work and you thought they might not. But yeah, that's about all I can think of right now.
So running an Ethernet over a barbed wire, well, that is surprising for sure.
Yes.
All right. Well, I guess we could end with just the final. You already mentioned AI, already mentioned a few things, but looking forward in the very near term future, let's say even a year or so, what are you keeping an eye on in terms of the industry or simulation within the industry?
So without trying to beat a dead horse, I think there's one particular bullet within AI that is going to get real exciting, and I think that's agentic AI, the ability for with the addition. So, not only just traditional neural networks that have been around for decades and decades and everything, but now with the proliferation of LLMs, the ability to perhaps have an LLM not just act as an interactive chat, but actually have more understanding and autonomy to be able to run the tools itself. I'm very excited about that personally. And then I guess there's one other topic I'm excited about, and maybe 1 year is too short of a time frame. But I'm really excited also for where open source or low cost simulation tools come into play. One of the big challenges in simulation is that the tools cost a lot of money. They're very expensive. It can be a limiting factor for small companies and everything. And so I have been trying to keep an eye on what technologies come out in the area of low cost or open source tools that can be used to do SI, PI simulations as well.
Well, Stephen, thank you so much for your insights on this episode, and thank you for joining.
Thank you very much. Appreciate it.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, QuantScience. For more information about our multiphysics simulation platform or quantum algorithm research, visit our website at quantscience.com. Thank you again, and see you in the next one.